Welcome to this third webinar of the series of 6 we're doing for the VELUX Project Development Guide. My name is Thomas Grebeck. I'm from GRAPHISOFT Center Denmark, and together with me I have my colleague Thomas Nyman Jensen. And we're going to talk about MEP modeling, structural modeling, clash detection, and also hybrid ventilation today. So it's a lot of technical engineering stuff as part of this project development guide. The last 3 weeks we've been doing webinars about sketching, about detailing, and we are moving along. So that's the last 2 weeks. So we had 2 webinars before, and this is the third one, and we are getting more and more into the technical parts of the project. And let's jump right into it because we have a busy schedule today. We're also having another guest, Shivani Motaka from VELUX, who will tell about natural ventilation. So I'll just share my screen, and once again, welcome. Quality through structural and MEP hybrid ventilation design. There's a screenshot from the MEP part of our small project. Outside what I told you just a second ago, we'll also be talking about OpenBIM. We'll be seeing how we can optimize the structural part of the building, jumping between different applications. We'll do not only the MEP modeling, but also documentation, clash detection, issue management, and hybrid ventilation. And hopefully we'll have time within the hour to answer some questions in the end. So the whole basis, the whole foundation of this webinar is the VELUX Project Development Guide. And the idea is that we have taken inspiration from an already built project, and we have redesigned it. It looks more or less the same, but changes has been made so it fully complies with the Danish building regulations. And the project is called Home for Life. It's built outside Aarhus, designed by Art Architecture and Espesen Consulting Engineers, and it was built back in 2009. And it's a really great building. The more we get into the details of it, the more amazing it is. When it was built, it was already a landmark for sustainable housing. And with this project, we're kind of updating some of the technical parts of it so it complies with the new LCA demands and other parts of Danish building codes. So to talk about structural optimization, we have gotten some help from Ákos Restrich. He's working with FEM-Design in Budapest, and because it's May 1st, he couldn't be at the live webinar, so he sent us a video, and I will play that now to show you how you can take this structural model that was done with the detailing project that was shown last week and try to optimize the dimensions of the different structural members. Oh, before that, I just want to run through a little bit about the OpenBIM part, because it's really important that it's fast and easy to share the model between different disciplines, between architects, engineers, landscape architects, and so on. And for that, we have international standards. Those are called OpenBIM in general. And some of the standards are the IFC file format, which will take the whole BIM project with all the 3D geometry and all the information and move it to between different software platforms. But today we'll also be introduced to a file format called SAF, which will take the structural analytical part of the project and move that today to a structural simulation application called FEM-Design. And then after the optimization and the documentation of the structural part, it will be moved back to ArchiCAD. So we have this going back and forth. And the great thing about OpenBIM and these international standards is that it will let you choose the best softwares for each specific task. So now I'll give the word to Akash from FEM-Design.
Hello everyone, and thank you for the opportunity to join this webinar. My name is Ákos Rektoris and I work at TrueSoft. For many years, I have been working with BIM collaboration, open standards like IFC and SAF, and data exchange between modeling tools and structural analysis tools. This has included product management roles, both ArchiCAD and FEM-Design. Today, I would like to show a practical workflow between ArchiCAD and FEM-Design. And more broadly, it is also a story about better collaboration between architects and structural engineers. To start, let me briefly compare IFC and SAF. IFC is used to exchange the physical building model between disciplines. It is very useful for coordination and reference models. It is well established and widely supported. SAF is different. It is used only for the structural analytical model, so instead of sending full physical geometry, we send only what is needed for analysis and design. It is newer, but already supported by most structural tools in Europe. The goal of structural collaboration sounds simple. The architectural physical model should be transformed into a structural analysis model to calculate and optimize its members. With IFC, the analysis software usually has to interpret the physical model and rebuild much of the analytical logic. With SCF, the analytical model is already created inside the design environment. Much of that work is already prepared before export, so the analysis software can focus directly on calculation and design. Today, my presentation will focus on this SCF-based workflow. In ArchiCAD, together with BIM Cloud, architects and engineers can work on the same model as a team in a controlled and collaborative way. The structural engineer can review the model, define the structural scope, and prepare it for analysis. ArchiCAD can then generate the analytical model automatically based on the engineer's settings and rules. This model is exported to FEM-Design through SAF. After the structural checks and optimization, the updated solution can be sent back to ArchiCAD also through SAF, and this loop can be repeated several times during design. After the structure is finalized, detailed design and documentation can continue in ArchiCAD or with models coming from other tools, for example through IFC. Architects usually model complex elements, for example layered walls and slabs. The structural engineers then defines which parts are load-bearing. From that, ArchiCAD creates the analytical representation. It also connects members based on rules, and the engineers can add supports, connections, and basic loads. So in the end, we get a structural model that is ready for calculation, not just a visual building model. That is exactly the kind of information SCF can store. Technically, it is similar to an Excel file, so it is transparent and easy to understand for engineers. Now let's look at the workflow that starts in ArchiCAD. Here we start with the building model. The first step is to classify elements by structural function. For example, this steel beam is load-bearing, but this other element, a timber item, is important for detailing but not for the structural analysis, so it is set as non-load-bearing. With one filter, we can show only the load-bearing part of the model. From this visible model, we can also decide which members should actually be included in the analysis and design. For example, here we activate beams and columns, represented in gray and brown, as structural members, while other beams, represented in blue, are left out of the calculation. After that, the engineer uses the structural analytical tools to define the analytical model, its connections, and its properties. The analytical members are generated automatically, but the continuity of the model and the load transfer can be defined by rules. For example, here the rule extends the columns so that they connect properly to the beams. These adjustments work within a chosen tolerance. In this example, the extension works if the element ends are within 800 mm. Next, we define the supports based on the real structure situation and the foundation concept. We can also define the end conditions of members, for example pinned, rigid or semi-rigid. Then we add the loads. This includes the automatically calculated self-weight. It can also include point loads transferred from other elements, and it can include surface loads, for example loads coming from a terrace layered structure or live loads converted from room functions. For automatic surface load conversion, we also need to define a temporary replacement plate. At this point, the analytical model is ready to be shared with other software. For SCF export, we can choose settings optimized for the target software, and we can map materials and cross-sections from the ArchiCAD project to the FEM-Design database. If needed, standard 3D profiles can also be created quickly in the project before export. Now we open the model in FEM-Design 3D structure. As a first step, we select the design code. In this example, we use the Eurocode with the Danish national annex. Then the analytical model created in ArchiCAD appears with its geometry, materials, and sections. Along with the SCF model, we can also import the physical architectural model from IFC as a reference. The model contains all the data defined and exported from ArchiCAD. The supports and the connections, the defined loads, the point loads, and the surface loads. The slab region used only for load definition in ArchiCAD can be converted here into what FEM-Design calls a covering. This allows the surface loads to be distributed automatically to the supporting beams below. The load combinations defined in ArchiCAD also come through SCF. And in FEM-Design, we can of course add more loads if needed, such as snow, wind, or dynamic loads. Now we can run the analysis, and we quickly get results such as internal forces, reactions, and displacements. By animating displacement, we can quickly check how the structure works together and whether the behavior looks reasonable. After that, we move to design and optimization. For example, we can optimize the steel beam and column sections within given limits. In this case, we don't want a deeper section than the one already used because of space limits, but we can allow other section types. The automatic design then searches for the best option based on utilization. After reviewing the results, like here the maximum utilization of the steel parts, we can update the entire model with the recommended cross-sections. We can do the same for the timber columns. We can also run automatic timber design to find optimal square sections. And in this example, the result shows that smaller sections are enough for the applied loads. And that means material savings, and in many cases also a lower carbon footprint. Next, we can generate the structural documentation. This can be done automatically from a prepared template. So the software can produce a full report that contains a representative cover, the final structural geometry in different views and details, load summary, and the final recommended sections and utilization results. Once the design is ready, we send the model back to ArchiCAD through SCF. Back in ArchiCAD, the model compare function helps us compare the current status of the ArchiCAD structural model with the model returned from FEM-Design. The differences are shown immediately and visually. For example, it is clearly visible that the structural engineer recommends a wider steel beam profile for one beam than in the original model, while a smaller profile for all columns. We can also review the changes by objects in a list, including details such as changed profile sizes. And these changes can be turned into issues and shared with the other project participants. Each issue stores the model view, the related elements, and the comments, so the responsible designer can find, follow, and accept the change requests easily. The designer can then update the project and the documentation accordingly in her working environment. And in this example, we can also see the value of optimization. A few members need to become stronger, but several others can become smaller. So the result is not only safe design, but also more efficient use of material. The key value of this workflow is not only that data can move between two tools, the real value is that architects and structural engineers can work in a clear and practical loop. Define, analyze, optimize, return, and update. This means faster iterations, better coordination, less rework, and often a more efficient structure. Thank you for your attention.
So I'm just blown away about this whole workflow. First of all, I can't understand that the BIM tools automatically models this analytical model within the geometry that I model as an architect, that it can so easily be imported into another application that does the whole model with all the technical part, that FEM-Design can again automatically just optimize the different structures and automatically build the whole drawing documentation and send it back. And this whole issue management part, that it's easy to see what changes has been made and assign the changes to an architect that can update the geometry in the model, so everything just works. This whole workflow, I think, is really strong, and I can't believe that an application like FEM-Design that I as an architect doesn't use can be that powerful. So thank you to Ákos Rektorich from FEM-Design for showing us this and for working with the project together with us, so we could update the structural project within the development guide. And I just want to note that one thing is that we had smaller steel structures now after the optimization, but we actually also have chosen to use reused steel beams for the project, so the LCA will be even lower because of this. And that will bring us to the next part of the webinar, and I'll just unshare my screen to give room for Thomas. And we have had help from an external engineer, an MEP engineer from the company Yokani, helped us do the 3D modeling of all the installations in the project for ventilation and plumbing and a little bit of electrical installations also. Thomas, I can see you have shared your screen. Would you take us through the project? And please note that Thomas is doing this live, so there may be some problems along the way, and that's just to show you how easy it is to correct those problems.
Yes.
Right?
Yeah. Sure. Let's see.
Fingers crossed.
Yeah. Okay. Thank you, Thomas. So this is the project as you've seen before and as shown at the latest webinar. But now we have some MEP systems already installed within the model and modeled as a 3D model as well. So first of all, the project, as you've seen it before, I actually also showed it last week with a sneak peek to some of the MEP systems. So now, just briefly, I'm going to switch to another layer combination that's called MEP only. So you'll turn off everything except for the MEP elements. So in this view, you can clearly see the floor heating systems, and all the pipes here are connected as one system. We have a little bit of floor heating on the bathroom on the first floor. We also have a ventilation system and of course sewage and drainage systems. I can click on these systems and see how all the pipes are connected into one system. Now, the systems have been defined in advance before starting the MEP modeling. By defining the system, you can define, well, name and graphic interpretations of that system, but you can also define routing specifications as to how many degrees each bend should be able to bend within different systems and pipe measurements. So the whole thing is built into ArchiCAD, and I'm just going to switch to my MEP Designer profile so you can see what that is all about. So I'm going to switch to MEP Engineering Profile, and now my toolbox is turns into ventilation shafts, pipes, and cable carriers. Now, if I click on MEP Systems, you can see the systems that have been defined already in the project. So these are the systems that we've been using, and I can create new ones, I can rename them, I can define the graphical interpretations down here, and define the systems that I need within.
And a system will make sure that everything is part of one flow. So
yes. So I can later on detect elements within one system. I can find the start point, the end points of systems. I can also look for blind openings, so parts that have not been connected, or open parts where you need to place a duct or an outlet or whatever at the end of a string within one system. So I can also go to route specifications, because when I'm creating these systems in my 3D model, I can actually just draw them as 3D pipes and drag them along in my model between the walls and the floors. But by doing that, I want to make sure that I follow certain, well, not regulations, but the specifications of the elements that will be available in my region. So if I go to the pipes, I can switch between different library types or specifications. So if I go to sewage outside, I can see for the straight segment, I have some types defined here. I have a DN of 100 and 110, and I have the actual millimeter defined out here. So this will determine how I will draw or create the 3D straight pipe segments. Moving on to the pipe and the elbows, I will go and look at the same system again, sewage outside, and I'll go down to, let's say, the specification DN, which will actually have a diameter of 110 millimeters, and I can define how many different bends I will have in my routing specification. I can define these myself, so I can add or delete more bends to each diameter or to a DN standard. I can create several systems for different pipe materials, and this will help me create a correct MEP system within my BIM model.
And when you say correct, something that can be bought and built?
Yes, something that can be bought and built that exists in reality, and you can actually make a quantity takeoff and simply just, well, go shop the parts that were added to the project. Yes, so I'm just going to show how that looks in the end, because a few drawings have been set up already. So here we have a drawing for the drainage plans on the foundation plan and on the ground floor. We have a drawing showcasing the floor heating. I'm just going to turn off my trace reference so that will not be confusing. So I both have the 3D view, I have the floor plans, and I have a little description and a legend showcasing the symbol, showing the symbol of the MEP systems within these drawings. So drainage plans, floor heating, water supply, it just needs to update because
it's a live project.
It's a live project, so it will analyze my MEP or my BIM project and show what has been determined up here. I'm just going to turn off my trace reference again. Thank you, Thomas.
I think it's really nice to have this 3D image on the drawings. So sometimes it can be really confusing if you only have plan drawings to figure out what goes where and what is this really representing. So this small 3D sketch where you have a ghosted structural building and then you can see the MEP systems that are on the drawing, I think that's a big help understanding drawings.
Yes, and it's quite easy to make because it is actually how the model looks, and this is where we generate the 2D plans from. So this is the actual 3D project. It has simply just been stored as a view, so I can add it to my layout. From this model, those floor plan has been generated as well. So these will be the same systems, and if I change any of the pipes, of course it will update on all the drawings where they're showcased. Yes, so just to give you an example, I will switch to 3D and I will go back to my 3D view where I have all my MEP systems. And I will look at my sewage system, and I'm just going to make a small copy of this pipe. So I'm going to place a new one 1 meter apart from the original one, approximately. And I'm going to pull it a little downwards and backwards. And I'm going to connect these two systems. So I'll simply just pipette this pipe to create a new one similar to the one already existing. And when I try to connect to another similar system, ArchiCAD will give me the possibilities of an automatic connection based on routing specifications. So using the arrow keys, I can switch between the 5 different solutions that it will propose to me in this situation. So I'm just going to select one of them and hit enter, and it will automatically connect the 2 pipes. Quite easy. If I want to do a collision detection between all these elements because they are inside my actual BIM model, as said before, I'll just switch back to the 3D overall view where we can see the whole thing. So now the MEP systems will be hidden inside the building. But how about clash detection, and will it fit within the load-bearing system of this building project? So we have a built-in feature called collision detection in model check. So I'll just open this dialog to prepare a collision detection, and I can choose between predefined criteria sets. So the point is that I need to set up different criteria as to what should be detected against what. So in this case,
So you're defining two groups.
yes,
That you fight.
they will fight
one versus the other.
Yes, exactly. So I can define whether it should be all parts of the model, whether it should only be MEP models, whether it should only be elements placed on a specific layer or elements with a specific name. I can define the criteria for the first group, and I can add different criteria here. So it could be element ID, for instance, and I can write what the name of the ID should be, what it should contain, smaller or higher than if it's a numerical value. I can do the same with the second group. So I can define these two groups quite specifically. I've cheated a little, so I've already created a ventilation selection and a wooden frame selection, and now I will have ArchiCAD run the collision detection. And
MEP versus wooden structures.
yes, and I thought that we cleared this already, but apparently there's still some things that needs to be checked.
There always is.
Always is. So here's two clashes. I'm just going to double click on the first one. Then ArchiCAD will select the elements. They are hidden somewhere inside the building, but with a quick shortcut, I can highlight and select only the selected elements. So this is where my clash detection is. And I can see quite obviously that this pipe needs to go through this beam.
So just to take that one more time, so you double click the issue, it would automatically select the two objects that are clashing.
Exactly.
And then with a shortcut, you could turn off everything else, so you only see the two problematic parts of the building.
Exactly.
And then you have to figure out if the structural engineer should move the structure or the MEP engineer should move the installation.
Yes. So I'm just going to do it once again, since you've asked. So I did the collision detection automatically. It detects these two clashes. I'm just going to double click on the first one. It will select the elements that are part of this clash.
And zoom to the right spot.
Yes, and they are somewhere inside my building between the ground floor and the first floor. So how to easily locate these and to narrow down the model view, I will simply, in this case, press F4. That means show selected elements only. And I can now see the selected elements solitarily in my 3D view. So I'm expecting that we won't have space enough to pull this pipe above underneath this wooden beam, but I'm guessing that we could cut a hole through it. So now I'm going to select this pipe, and I'm going to right click, and I'm going to say connect and say create openings from selection. Now this dialog will appear, and I can determine how ArchiCAD should automatically generate holes in the clashing elements. I can also write a tolerance to give it a clearance space. I think 15 millimeters. It's not that big, but we don't have that much room, so I will just say create opening with these settings, and now ArchiCAD automatically creates a hole in the wooden beam. So now we won't have a clash anymore. I'm just going to delete this clash because I'm pretty sure I fixed it already. I'm going to switch back to my 3D overview to have a look at the entire model, and I'm going to check the next clash. It is somewhere deep inside the building, so I'm just going to use the same shortcut to highlight this reservation and see what this is all about. So here's a drainage pipe going through a wooden beam, and I'm expecting that we're allowed to cut a hole in this beam as well. At least that is what I'll do now using the same technique. So selecting the pipe, and the openings dialog is already open, otherwise I should say connect, and this will appear automatically. I'll say create openings, and now ArchiCAD automatically creates a hole with the 15 millimeter clearance around this pipe. If it were to intersect multiple elements, it will create openings in all the elements clashing with this pipe. So
there's a reason that normally these issues are managed at a meeting with the complete project team, so the engineer can also take part of this discussion if this should be an opening or if we should route the MEP system outside the structures.
Exactly. I'm just going to do the collision check again to see whether it will find any more collisions after I've cleared these ones. created holes automatically within the beams. So now from my model check and my setup of the collision detection, it will not detect any more collisions and I'm good to go.
Wow.
That was fast, but we only had 2 clashes. So somebody has been through this before, I guess. When having these MEP systems, they naturally consist of several different parts, and it would be interesting to see how many parts are in the system. So I've cheated a little and created a small schedule. I can create schedules that serves as quantity takeoff in ArchiCAD by simply, let's just see, it's just thinking a little, that was the wrong one. So I'm going to go to Elements and say New Schedule. And in here, oh, sorry, I could create a schedule. This is not going to be the right one. I could define a criteria that will select the different elements. So in this case, it could be MEP elements from a certain layer with a certain name. And I can determine what I want to know about the selected elements on this schedule already. But I've cheated a little, so I'm just going to open a list called the ventilation parts list. And in this case, I'm asking ArchiCAD to list everything on the layer V573 for MEP, that is the ventilation layer. I want to know the library part name, the MEP system, the length, the diameter, and the quantity of all the parts. So after doing this, ArchiCAD will generate this schedule, and I'm just going to resize a little because some of the graphic looks a little off. So I'm just going to resize the columns and the rows to fit my content. I'm going to extend the zoom so I can see how much it is. And now they are listed based on their diameter, so I can see the different parts, what system they belong to, and the length of each and every element. Now, all in all, we have 31 meters of ventilation pipes, and I just want to highlight the values. I'm just going to edit the grand total and make it bold and give it an underline. So now we can easily see how many meters of ventilation ducts we need in this project.
So to take something from this would be to talk about reuse of data. So a lot of people would say, oh, on a small project like this, it doesn't make sense to model MEP, or it doesn't make sense to model the structures, or it doesn't make sense to do a simulation of structures because it's so simple. But the whole point, perhaps the whole point of this project development guide is that it's actually faster to model and then reuse. So by modeling the installations, it's drawn on the plan drawings. That could possibly be done faster just in 2D. But then you get this 3D overview on the drawing that actually has a purpose and a value. But then we reuse that data, the geometry, to do the clash detection and use that for the issue management and also for the quantity takeoff. And I was just talking to an installation company 2 days ago that says when they're giving an offer for a job, they start counting on 2D drawings. And that takes longer than just to model in 3D and automate everything else. Every time there's a change, everything updates automatically. We can redo the clash detection. We can move the openings if needed. And we can check as a virtual prototype of the building if this would work in real life. And that will not only give us less work, better buildings, but it would also mean that we're using less material. We are doing fewer mistakes on site, and that has a sustainability side also. So I think it's really amazing to see how easy it actually is to do this in 3D.
And actually in this specific project, even though it's a small one-family housing, then the ventilation system has to be placed quite carefully because it needs to go through very narrow corridors and construction parts. So creating the MEP system in 3D, well, it might take a little bit longer than just drawing it as a diagram on a 2D plan, but what you get in return is a huge amount of data and well, a 3D geometric analysis of what is actually possible and how it should be placed. So you don't have to redo the system, you don't have to figure it out on site, you can plan the whole thing in advance, and it only takes a little bit longer to create it in 3D, but you get all this from it, both the quantity takeoff and make sure that you can fit between the construction and the load-bearing part. So in this actually project, I think it would be a very good idea to do the 3D modeling of the MEP system.
Always. So just take a look on this image on the screen right now and see the ventilation project. Thomas, feel free to unshare your screen because we're gonna have a small change in guests right now. And while Shivani will take over Thomas's place, please remember that this ventilation part that was just modeled will be part of this hybrid ventilation discussion that we're having right now. So in the project, there's several parts modeled already. There's the mechanical ventilation system, but there's also a lot of special windows that works together with the mechanical ventilation as natural ventilation. And if you optimize that combination, it really has a lot of benefits, saving energy on the project and improving the indoor climate for the project. And welcome, Shivani, and thanks for joining us to talk about hybrid ventilation. Next topic will be the introduction to indoor climate and comfort.
And now we're moving into introduction to indoor climate and comfort, where we bridge the gap between design and human experience. So building on this foundation of indoor comfort, let's talk about the why and the how, specifically why ventilation serves as fundamental infrastructure of a healthy environment. So beyond comfort, ventilation is required for a healthy space. So it isn't just about fresh air, it's about protection, and proper airflow actually prevents mold, respiratory issues, and also overheating. And our approach is actually centered around hybrid ventilation, where we combine the natural airflow with mechanical systems, and then we maintain a good indoor air quality the whole year around. And simultaneously, as seen in the bottom diagram, we also use cool outside air to regulate thermal comfort. Now we can talk about the next strategy. So building on the seasonal strategy that we just discussed, let's look at why maintaining a good air quality is so critical in modern construction. And as you can see in the image, airtight homes are actually a very excellent solution for energy efficiency, but they also create a paradox for trapping CO2. In smaller rooms, for example, which are used for sleeping or studying, levels can easily skyrocket to 1500 ppm to about 2500 ppm. And this is actually far surpassing the 950 ppm threshold, where we see impaired cognition and disrupted sleep. This is actually very important because elevated CO2 causes fatigue, headaches, and reduced cognitive performance, which directly impacts school achievement during critical development phases. Crucially, as the number of people in a room increase, the CO2 actually builds up even faster. So in these moments, natural ventilation is actually our best ally, as it can flush the space and reduce the CO2 levels much more rapidly than mechanical systems alone. Now we can understand why clearing CO2 is so vital for health and performance. Let's look at the most effective ways to actually achieve this air renewal cycle. If we look at the far left image, we see a standard mechanical system where, even though it's reliable, it typically takes about 0.5 air changes per hour. And in practical terms, this is actually nearly 2 hours to actually fully renew the air in that space. So when CO2 levels are actually spiking, due to high occupancy, 2 hours is simply too slow to maintain a healthy environment. This is where natural ventilation through facade and roof windows becomes a game changer. By simply moving to a single-sided window, we can double it to more than 1 or 2.5 ACH, reducing the renewal time to under an hour. Moving further to the images on the right, we see the real power in a very smart design. So cross ventilation and stack ventilation is where we can use the natural buoyancy of the warm air that is actually rising up, and this can hit about 2.5 to 5 ACH. So we're now talking about a full air cycle in just 12 to 24 minutes. Finally, the most effective strategy is the stack effect, which is combined with cross ventilation, which you can see on the far right. And this is where you can see high levels of almost 10 ACH, and this allows us to completely flush out the room and reset the CO2 levels in just 6 minutes. So the key takeaway here is quite clear. While mechanical systems provide a baseline, leveraging natural ventilation through smart window placement actually allows us to react to poor air quality almost instantly, ensuring that we maintain a healthy and indoor climate, as we actually promised at the beginning of the presentation. Now I can quickly take you through the different ventilation metrics that could be beneficial to know about. When evaluating mechanical ventilation, we focus on constant variables, which is the airflow rate. This is measured in liters per second or ACH. The energy consumption of the fan power, and the efficiency of the heat recovery, which is measured in the percent. Now, as we transition to natural ventilation, the metrics is actually more dynamic. So we have to account for the fluctuating outdoor temperature and the different climate conditions like wind speed and direction, along with the physical opening and size and position of the windows. Now in the last column, as you see, this represents the hybrid approach, which is where the true optimization is actually happening. Here, our key metrics includes the switching strategy. This is deciding exactly when to move between the natural and the mechanical modes of ventilation, and the control strategy as well, which can be fully automated or based on real-time occupancy levels. In a hybrid system, we monitor this closely because we want to minimize mechanical runtime whenever the outdoor conditions are actually allowing for free natural ventilation. Now, we've just broken down the technical metrics and performance data of these systems. Now let's look at the bottom line. How can these strategies translate into real-world savings across different climates? This slide is actually highlighting the most energy-efficient solution we have. So looking at the bar chart, we see that in every single city, the hybrid model outperforms a pure mechanical system. So basically, by intelligently switching between these two modes of ventilation, we can reduce the energy demand without sacrificing the indoor comfort or even the air quality goals, which we've discussed throughout this presentation. Now we've looked at the energy savings possible through hybrid ventilation systems, but we also have to contextualize this within our changing world. As we discussed in our first webinar, where we were talking about the cooling demand in buildings, and this is projected to triple by 2050. So this also means that we must actually move beyond simply adding more machinery and start designing smarter for more resilient and sustainable homes. And as you can see on the slide, we have two paths to actually tackle overheating. We can rely solely on active solutions like air conditioning, which significantly increases the energy load, or we can prioritize passive solutions. So by utilizing external shutters and hybrid ventilation for ventilative cooling, we can drastically reduce the strain on the mechanical systems. So our second solution is actually rooted in the adaptive comfort model. And this model is recognizing that the acceptable indoor temperatures aren't a fixed number. They actually vary based on the outdoor conditions and the temperatures. So when occupants have a personal control like opening a window or adjusting a shutter, they maintain a higher satisfaction level even at higher temperatures. This essentially closes the cooling gap. So it's important to note that the regional context of these strategies are very important. So for milder summer climates like say Copenhagen or Munich or Paris, these passive measures can often eliminate the need for air conditioning entirely. However, in much hotter climates like Italy or Spain, these passive strategies remain vital to reduce the load. Some level of air conditioning would still be required to maintain comfort during extreme peak hours.
Yes, and as we learned in the first webinar 2 weeks ago, we saw in this microclimate analysis around the building that the cooling demand is actually supposed to rise with 2.5 times the current status. So we'll have a much higher cooling demand in the future. But in Danish climate, it's still not that many days a year where we have this problem. So if we install cooling system, air conditioners, as more and more people do in Denmark, they're actually a huge technical installation to solve a rather small problem.
Yeah.
And today we already have windows, and windows also bring light and fresh air and visibility to the outside. So it might make much more sense to make great architecture by placing windows in the right spaces and the right kind of windows instead of trying to fix everything with mechanical systems.
Yeah, and you're absolutely correct actually. This is exactly the point that we want to touch, where we're reducing the load on mechanical systems in these climates where you can actually use passive systems to reach a desired amount of satisfaction indoors. So that's a very good point actually.
And I'm learning more and more about the VELUX product portfolio, and there's this whole smart home thing with all the sensors inside that will see temperature and humidity and CO2 values, and they will actually automatically open the windows when needed.
Yeah.
So that's really clever.
And we are going to touch upon these topics a little more in the next few slides, which would be discussed by my colleague. But just to wrap this up before I pass it to my colleague, I would like to say that at VELUX we do believe that a building's primary function is to support the health of its occupants. So throughout the session we've demonstrated that high quality indoor climate isn't just an add-on feature, but it's a baseline requirement for long-term well-being. So, yeah, and now I can pass it on to
Elham Big.
Yeah.
Yes, and Elham is your colleague, and unfortunately she couldn't be here today, so she's part of the next few slides as a video presenter.
Mm-hmm.
Hey everyone, I'm Elham from VELUX and will be here with you for this part of the webinar. I will talk about the workflow and methodology used in this project to assess indoor climate performance, and then show some of the key results from this assessment. So we started with our BIM model created in ArchiCAD and transferred it into iDice to do simulation. This transfer can be done either through an IFC export of the BIM model or by exporting the model to SketchUp first and then to iDice. So they are different workflows and you can choose based on your project. And when we do so, the 3D view of the model in iDice basically look like on what you see on the right side of the slide. All the spaces in the house are associated with a zone in IDA, which make it possible to assess the performance of each zone. Coming to simulation logic, we define a specific number of people in a zone and their presence schedule as well. There are set points for automated operation, meaning, for example, in terms of opening the window, there are some assumptions. In this case, the windows open when the temperature inside gets to be warm and the outdoor temperature is not too warm or too cold to allow air to come from outside to inside. The same for external heat protection. They get activated when the indoor temperature is getting warmer and we simply need to stop the heat gain from the windows, and then external heat protection are activated. These all matters because they can heavily influence the indoor performance results. And regarding the simulation period, in this project we are focusing on the summer period from mid-May to mid-September. This allows us to evaluate how natural ventilation and shading strategies can improve indoor comfort and reduce overheating during these warm seasons, and helping to have less energy consumption through active systems. Okay, now let's look at the indoor air quality in one of the bedrooms. As an example, we selected a typical summer day, in this case the 29th of July, to examine the results in more detail. Talking about indoor air quality, of course it matters when the windows are open and allowing fresh air coming in. And we can see on the first graph on the left side how the windows perform based on the set points defined in the simulation. So looking at the VELUX roof windows, they are open around noon and remain open for part of the afternoon. And the second graph next to it shows the immediate impact on indoor CO2 concentration and relative humidity in percentage. We can see when the window opens, the CO2 level drops from around 860 ppm to around 313 ppm. This shows the clear benefits of bringing fresh air into room through natural ventilation. To understand whether the bedroom stays within a good indoor air quality range during occupied hours, we can refer to standards. In this case, EN 16798-1, which reflects different levels of expectation in terms of air quality from high to medium, moderate, and low. Based on the table on the right side and the CO2 concentration achieved in our simulated bedroom, for us the result falls within category 1 for this selected date, but it could be on other days falling into category 2. But both categories 1 and 2 are considered recommended indoor air quality categories. Okay, now let's look how is the level of comfort in the living room as an example. Again, during the simulation period, which is from mid-May to mid-September. On the left side, you can see the living room zone simulated in IDA. The simulation includes external shading activation and ventilative cooling when it's needed. There is no active cooling in this case because the project is located in Denmark and simply there is no need for active cooling due to use of natural ventilation and ventilative cooling and also external heat protection strategies, which are sufficient to provide a good indoor climate, and we can reconfirm this based on the simulation result. So the graph on this slide shows the operative temperature in the living room over this full summer period from mid-May to mid-September, as I already mentioned, and the background color in this graph represent the 4 comfort categories based on the adaptive comfort model. To just explain very simply what is adaptive comfort model, basically this model considers that people can adapt to seasonal outdoor temperature changes, meaning we may accept slightly warmer indoor temperature in summer and a slightly cooler temperature in colder periods. And in our case, the living room has around 2,900 occupied hours during the simulation period. And we need to check how many of these hours falls under overheating hours. And there are just 12 hours in the uncomfortable range in terms of thermal comfort. This number of hours equals to just 0.4% overheating hours. And according to adaptive comfort model, at least 95% of the occupied hours should meet the comfort criteria. And in this case, our results clearly are within the comfortable range, showing that living room performs well in terms of summer comfort. And we can say the living room maintains a good comfort level during the summer with very limited overheating hours, using external shading, ventilative cooling instead of active cooling. And this means that the comfort result could be achieved through passive and low energy strategies.
It's apparent that there's a lot of benefits to adjusting the indoor climate with natural ventilation first. And especially skylights has a lot of special features that will help this. And in combination with this automation that will automatically open and close the windows, pull up and down the shutters, I think will greatly lower the demand for mechanical cooling. We all know, in Denmark at least, in the summertime when we come home and the whole building is just too warm, the first thing we do is to open windows. But if it's too hot inside, it will take some time with natural ventilation to bring down the temperature. So if there's an automatic functionality, especially in skylights, that can take in a lot of heat, that they will close the shutters when needed and they will open to have a little bit of airflow through them, then we'll not see this too high heat level inside the building. So it's about choosing the right kind of products, but it's also about being clever as an architect to figure out how to have these connected volumes within the building that will allow for a stacked ventilation system. So to zoom out a little bit here in the end, we have been talking about structural BIM, why it makes sense to have this analytical structural model within your BIM model. It doesn't take much time to add it when you have a structural model with the geometry already. With OpenBIM and international standards, it's easy to move the information from your BIM application to simulation applications like FEM-Design. That will allow you to not only document but also to optimize the structures. So we will save on material and therefore save on CO2. Modeling the MEP systems also, all the installations, that will be the groundwork for producing drawings that will be easier to understand because you also have the 3D illustration trying to bridge between the kind of abstract 2D drawings. And for installations, often they're placed on top of each other, so a 2D drawing might not be the best way to understand the MEP system, and a 3D is. And when you have this 3D model, it's easy to add value to your project by reusing the data for clash detection, for example, and add that to a workflow of issue management, so we'll have fewer problems on site. Everything will be made so it will fit, and we don't have to have solutions of problems that will bring down the quality of the building. And then we had a really nice introduction to why natural ventilation will add on top of the mechanical ventilation for this hybrid ventilation theme. That will be the best of two worlds, making it easy to fast cool the building and ventilate for high CO2 impact. So in the end, this will bring the quality up. We have almost at the end here, because we're continuing. So this one is the third webinar. The fourth webinar will be next Friday, and we'll talk about life cycle assessment. And the life cycle assessment, also called LCA, is the climate impact of the project, and we'll be looking at energy and material CO2 and try to limit those. That's all I had today. We've been through a lot of different discussions. Thank you so much to Thomas Nyman Jensen, to Shivana Mutaka, but also to Alberte Grosdal-Bønde and Lorena Jelinek, who has been behind the cameras. And thank you to all of you staying for a whole hour just watching this webinar. I hope to see you next week. Bye.
See you. Bye.